So I'm going to start immediately with this high-level view of Shor algorithm. And don't be scared. I'll just go slowly after that. Okay, so just the high-level view, and I think it's very important. So this is the sketch of Shor's algorithm. And if you just look at Wikipedia or Qiskit or whatever, you'll find something like this. So it starts with a quantum superposition. So you think of it as creating a whole bunch of possible inputs. Then you have the function of interest. So whatever this block that's UF, this is the function of interest. So this is a completely classical block. So you can kind of use your whatever language you want to do, like classical reasoning, to write this big block in the middle. So this block here does modular exponentiation. So you can kind of write, if this was like a function program, this is a two-line program to compute the modular exponentiation. But you have to do it in a special style, whatever, but that's no big deal. And then there is a Fourier transform. Okay, so these are the three blocks that you see in Shor's algorithm. Now here's the algorithm on top of here. Now, this algorithm supposedly has an exponential speedup over the best classical algorithm we know. Okay, I mean, it is on paper, there is a proof that this is exponentially faster than anything we know how to do. So where is the speedup coming from? Okay, so if you look at the pieces, so there's three pieces, right? The U block by itself is classical. So that by itself is just nothing going on there. If you look, if you try to take H and U, the first two things together, and you stop there, that's completely boring, and it also can be done classically. Why is that? Because you're generating a bunch of choices, which is the H, creating a bunch of superpositions, and then you run them through this F block. And if you stop there and you measure, you will get a random pair of input and output. So you don't, I mean, you can just do it classically, and it's like one sample of this function. So H and U by themselves do not give you any power. A common thing that people say in the literature is, okay, the magic comes from the Fourier transform. But there is this paper that sometimes is not, kind of well known for some reason. But the Fourier transform by itself can also be done classically, simulated classically. So we have like three pieces, and it's not clear where the advantage is coming from. It's not obvious where it's coming from. If you look at each piece separately, there is no obvious place where you can point and say, this is why it's faster. Another common answer is, well, it's at the interface between them, because it's not, the speed up doesn't come from any particular block, but it comes from how they interact. So a common answer is that when you get to barrier 2, there is some kind of deeply entangled state, and that's why you have a speed up. But again, there's other theorems that say this is not sufficient. You can have very entangled, highly entangled states, and you can still do classical simulation. There's no speed up. So to add to the confusion, there is that well-known theorem. This is from Shi and Aharonov, well, two different people, but they build on each other, that say that a classical universal gate, which is Toffoli, which unfortunately is written T here, it's not it's just the way, I don't know, it's not supposed to be T, it's not a good name for it. But anyway, that Toffoli gate, which is classical universal, plus one gate, which is the Hadamard gate that does superpositions, which we saw in the first slide. These two are universal, up to some approximation, which is kind of not important for now. So where is the speedup coming from? So CCX, which is the good name for Toffoli gate, is classical. Hadamard by itself is not that powerful. It just creates superpositions. But somehow the combination is faster, or is believed to be faster. We believe there's a quantum advantage from this combination. So this is like a big kind of open question. Obviously, this is what everybody's trying to understand in some way. Okay, so if I knew how exactly the speedup comes in, I would probably not be here. I'm probably getting a prize somewhere. So I don't know. But I have a new perspective. I think there's a new perspective that I can give you. And after kind of looking at it, it's not quite new because, as usual, somebody else did the work you thought was new a few years ago, and we'll see that in a second. So I don't think anyone here, well, maybe somebody was in the community long enough to know this person. Anybody know this one? Perfect. I'm glad one person is there. Because otherwise I would feel very old myself. But I am old, but that's a different story. So when I started my PhD, there was all of these arguments on the Scheme committee. And people were involved in fighting or whatever. And he has very, strong opinion. So he was one of the original designers of MIT Scheme. And I found this on the web. It's very funny. It was released in '86 as free software before the Free Software Foundation was founded. So it's like it goes in prehistory. Anyway, so why am I interested in him? Because he has a master's thesis from MIT, which was very hard to find. But he explains quantum, some observation of quantum mechanics, whatever, blah, blah, blah. And then there's Colsey in there. So that's my favorite. I mean, Colsey that I spent, I don't know how many years of my life doing Colsey. So something about continuations was somehow in his thesis to explain quantum mechanics. And I thought, well, maybe there's something there that is interesting. And I have to admit that I tried to read this thesis many times over the years. Every time I understand something, but I don't think I ever fully understood it. But I do feel that there is something, like a gem in there, because we know that quantum evolution is unitary, it's reversible, it goes back and forth. If you look at Feynman diagrams and if you look at various interpretations, you will find waves going forward and backwards. And so there is something about continuations or about going back and forth, about duality. And so maybe there is something there that is fundamentally as part of quantum computation. So that was my kind of goal. Let's do a fresh start. So as we've seen, we have Toffoli gates and we have Hadamard. Toffoli is boring, for this talk because that's classical. So Hadamard is the interesting thing. So we'll think of Hadamard as a choice. I mean, it's not a radical kind of observation. It's clearly gives you two options, like a superposition. You start from one state, you get two choices. So it's some kind of choice. It's not a classical choice. We'll talk about that in a minute, but it's some kind of choice. Now, but it's a choice that is very strange in many ways because you cannot observe the intermediate states. So this diagram is quite nice. I found this to explain what I had in mind. So if I have a classical language, you start with a classical value, this initial value here. You have a classical, so initial value is classical, final value is classical. But if you have a classical language, in between, you remain classical. You're either true or false, right? So you never have any kind of non-deterministic kind of behavior at all in the middle. In the quantum setting, you start with a classical value. When you measure at the end, you're classical, but in the middle, you have this unobservable superposition. So this three wiggly paths, somehow you are in a superposition in all of those three paths at the same time. You cannot observe those things. You start in the classical point, you end in a classical point. In the middle, you have these choices that are kind of not observable. And to make it slightly more precise, in quantum mechanics, quantum computing, These choices have weights and probabilities, and we'll see that in a minute. Okay, so let's pause a little bit on quantum, and let's talk about continuations and choice. So if, I don't know how many people played with continuations, but if you have, this is very familiar. If you haven't, I'll try to explain it in 2 slides. Yeah, I mean, come on. It's only my PhD and 10 years of. Okay, so let's kind of start with something simple. I have an expression x plus y times 5. I'm looking for the mic. I can like to talk, but I can't find it. So I have an expression x plus y 5, and I want to evaluate this expression, and I'm telling you x can be 1 or 2. There's a choice of what the value of x is, and there's a choice for what the value of y is. So you could, do a tree like this to draw what the evaluation, what the data structure is, if you wish, what the data is. So there is a plus and an x and y and a 5, whatever. This is the abstract syntax tree. But then the x can be 1 or 2, and the y could be 3 or 4. You can imagine building that tree. Thank you. So you can imagine building that tree to represent what the value is. If you have continuations around, you do not build the tree explicitly. And that's very important because the tree usually is very big, and you cannot even generate the tree. So what you want to do is you want to use continuations to implicitly build a tree. And this is very common. We use this. I mean, I think there's probably like 100 papers that talk about choice and continuations to explain this idea. But let me kind of first talk here about this idea here is you write just the expression, and then you write this choice, the expression, which uses the continuation. Yeah, here. So it uses this continuation. So what's happening here is this reset tells you the boundary of your choice, right? So this choice here is not going to be a choice that is visible to the rest of the universe. It's only visible up to here. And then what is the choice? It says, give me the continuation. I'll give you like a visual in the next slide, and copy it twice. So if I want to choose between A and B, I'm choosing, and somebody's using my choice. Somebody's going to, I'm making a choice, and somebody is going to, see my choice. And there's somebody who's going to waiting for my choice is that K. So I'm going to give K an A, and then give a B. And for this slide, I'm just appending the choices. So this is not quantum. This is just a classical kind of way of evaluating all the choices and kind of make a list of all the choices. So you run this thing in Racket, and you get the list of all the choices. Okay, so what's a little bit more detailed? This is my one explanation of continuations. Okay, so what's happening? So I copied the expression here. I inlined the choice. So you can see it all in one slide, one expression. So what's happening here again is if you start evaluating this, so there's a reset, okay, nothing happens, let, blah, blah, blah. The first thing to evaluate is that. So what happens is, so here this is the same expression, but I kind of colored a few things. So this shift says, what is K that is waiting for me? And the K is the dark thing here. And that dark thing gets copied and written twice here. So you'd see that reset, append, some big thing 1, some big thing 2. Reset, append, that's some big thing with a 1 and big thing with a 2. Okay, and that's how continuations work. I mean, of course, this is a textual representation of what the state is. That's not really what happens in a runtime system, but that's a good way to understand what's happening. And of course, there's another shift here, another reset here. So when you do this shift, you copy again, and you copy again, and so on and so forth. So you end up having, So this is not going backwards, this keeps going on because I'm pushing the wrong button. Okay, so continuation, go back to the continuation. Okay. Okay, so you all know about continuations now. Yeah, that's okay, perfect, thank you. Okay, so now let's go back to quantum. And what we're going to do is we're going to view Hadamard as making a choice and CX or CCX as just a boring kind of like plus computation. Doesn't do anything interesting for us. In fact, here's the semantics if you want to see. So CX, which is a special case of the Choudhury gate, it's just compute. It takes two inputs, computes something 0, anything is 0, whatever. 1 0, 1 1, 1 1, 1 0. Doesn't matter, whatever. Does whatever. Hadamard is interesting. It takes a 0 to 0 plus 1 and a 1 to 0 minus 1. And the sign is critical. So the sign is a relative phase between the two choices, and that's going to be very important. We'll see that in a minute. Okay? So now if I have a tiny, tiny, tiny circuit like this, I start with 0, 0. Then I have a Hadamard from the first one. So the first one becomes 0 plus 1. So I get 0 plus 1 on the first one. And then I apply this CX gate on the second. So 0, 0 goes to 0, 0, 1, 0 goes to 1, 1. And then there is this weights that I carry around the tree. Okay, so again, it looks, if you look at it, I'll come back in a second. This tree and this tree look very similar, except there's these weights that we have to talk about. So first, before I kind of jump in, just to recap what we have so far. We have a model of computation for quantum circuits that is Hadamard and Choudhury. Choudhury is classical semantics. Hadamard gives you choices, which we model using continuations. Okay, so here is like a bigger example that I want to use to illustrate an important point. So the example again is like nothing. We've seen Hadamard. You've seen these gates, more Hadamards. So the classical trees look like this. The quantum trees look like that. Not really any big difference at that level of abstraction, except there is these weights, and of course one is sideways, but that's just because I drew it this way. Okay, so but there's weights that you keep as you make choices, you keep multiplying the weights. So it starts with square root of 2, then another choice is 1/2, another choice is 2 square root of 2, and then 1/4, and so on. Okay, so there's these weights that are important. So hopefully this is, at least intuitively, you can see what's happening here. Okay, so what I didn't talk about at all is there's this funny measurement, things that we'll have to use to kind of make sense of this tree at the end. So the tree is generated, but all of the stuff supposedly not observable at all. You cannot observe any of that stuff. I mean, all of the stuff is the hidden intermediate states of superpositions which cannot observe. So what happens in the measurement? And measurement is a big, big, big kind of mystery. People kind of fight about it for 100 years. They were trying to understand what measurement is. We still don't understand. In fact, it's a postulate of quantum mechanics. It's not even, there's no justification for it, except smart people said it works, and it works. Okay, so it doesn't matter what this slide says, but in terms of the tree we have, this is what happens at measurement. These arrows now. So you look, for example, at one of the branches says 1/4 0 0 0 0. You look at this and you'll find, here's another 0 0 0 who's 1/4. So that gives me 1/2 0 0 0 0. And then there is another that says 1/4 0 1 0 0. And then you keep scanning and scanning, and you find minus 1/4 0 1 0 0. Cancelled. So these things disappear. Okay, and you keep going like this. So at measurement, that's what's happening. Is you kind of collect the various branches. Some of them interfere in a positive way, and some of them interfere in a destructive way. And so you kind of do this kind of interference, and you get your final results. And then at the end of the day, once you do this calculation, you square those numbers, and that's the probability. So this is the Born rule, which is a postulate. Again, why it works, I have no idea, honestly. It's a big mystery why it should be this way, but it is. So you square those numbers, that's probability. So with probability 1/4, you would get one of those if you measure that. But the important thing is you will never see 0, 1, 0, 0. Never. Okay, so this is important. Okay. So the first kind of maybe maybe insight is that instead of talking about entanglement or about Fourier transform or about this or about that, it seems that when you have lots and lots of these red arrows, this is something that will give you a quantum advantage. Because a classical way of sampling would be completely lost if you try to sample, if you looked at the branches individually, you would get no information. You look at this branch, you think 0, 1, 0, 0 is a possibility, and then you may find much later that there's another choice. And of course, this could be much more complex. You can have, many, many, many red things that eventually canceled, and you cannot see that no matter what you do classically. So this is like one possible kind of, insight here. The other thing, and this is a jump here, but I think it's an important. Even when you do classical continuations and classical choices on probabilistic programming, non-probabilistic programming in the classical setting, there's no. When you say choice, it's always kind of ambiguous. What you mean? There's internal choice, external choice. Who's choosing what? And so the internal choices are the ones you control, as in the code, for example. The external choices are the ones done by the environment. And they're different. They're very different because historically they're like angelic and demonic, funny names for them. But anyway, so the point is you have choices that you control, choices the environment controls. Now, this is a very, I love this this paper. I don't know if you know. So Conway is the Conway of the game of life. So this is the famous Conway, and maybe Cohen is not as famous unless you're in quantum. So this is the Cohen-Specker theorem, which is a fundamental theorem in quantum information. If you've heard of Bell theorems, this is a generalization of the Bell theorem, the Cohen-Specker theorem, not this one. Anyway, so this is a mathematician and a physicist or mathematical physicist, whatever. And they're kind of formalizing this idea of choice. And so they have, it's a very, very interesting paper. Actually, there are 3 papers and then some videos that the videos are very nice too by Conway. He's an amazing speaker. But anyway, so he talks about these choices and which choices are you can do as an experimenter and which choices are done by the particles, so to speak, and kind of explains, maybe this this idea by putting agents, who's making what choice when, kind of make it more. But anyway, so we don't need to get into that a little bit, or try to explain, things, by trying to kind of add interpretations. This is, as I said, 100 years of arguments in quantum, mechanics, but what these choices mean. Says even a top 10 list by Tom. I don't know who Tom is, but I thought it was interesting. But computationally, it is just continuations with these funny choices. So we can at least kind of do a computational model that makes sense. Okay, so here's what you're waiting for, some code. So this is a simulation of a full simulator. Well, there's one helper function because I was told that you have to have auxiliary functions. So there's one auxiliary function here. This auxiliary function right here, we'll talk about in a second. But this is a full quantum simulator. So there's 2 lines for CCX and Hadamard. CCX has 2 cases. If the controls are true, you negate. If the controls are not true, you do nothing. So here you negate the target if the controls are true. So this is the boring stuff, the CCX, because this is just Boolean negation. Hadamard is the one we have a choice. So you generate the choices, and then there's a collect, which will deal with how to manage the choices. So you generate the choices either with a -1 factor or a +1 factor, right? So these are the two cases. And there's no continuations here because this is all into the collect that will kind of hides the continuations and math continuations and so on. But this is a full simulator for quantum, this quantum language, which is CCX and Hadamard. And if you want to use the kind of boring non-observable thing that lets you look at the internal states, then you can use a list to represent the continuations, all of the continuations are correct in the list. If you want to do what the errors were doing by kind of summing the weights, then you can kind of put them in a hash table or something. When you see the same continuation, you combine the weights by plus, and you can kind of get the results you want this way. So that's it. And here is the shift, just a continuation. And then you make the two choices and either collect them in the list or collect them. So this is the not observable one. This is the quantum one. Okay. So that's it. That's the kind of technical part. So I didn't have a slide for this, but this is a very important point. I don't know how much time I have. I see Andy is here, so I don't have time. So it would be kind of okay. Let me actually say it. Give me 1 minute. Even quantum computing cannot always manage these continuations. You need special symmetries, special cases where there's certain patterns to take advantage of that, and try to understand when exactly you can take advantage of that is maybe the new perspective that you might gain from this presentation instead of some of the other approaches that explain quantum computing in different ways. Okay, I'll stop here.
Thanks.